Okay, so today's topic, we are doing applications of integration. Primarily work and center of mass. Which I'll just abbreviate COM. So if you ever see me write that, it just means center of mass. So what are the basics? Hopefully you've learned somewhere in high school, middle school maybe, that Newton's second law, force is equal to mass times acceleration. And somewhere, hopefully you've seen that work, at least on a basic level, what we want to consider as work is force times distance. So this isn't quite true, at least for work, even for this basic force equation, because if things are changing in time or over a distance, then our force is non-constant. So if the force is non-constant, we need a better calculus definition. Of work. And namely, where does that come from? Well, if force is changing, it's going to be changing with respect to distance. So I'm moving, or we have something changing, like stretching a spring, where as I change my distance, the force is changing on it. I'm getting a stronger force or a weaker force, depending on how we move. So in that case, our total work that we do, well, really what we want to do is add up all the infinitesimal pieces of work. And so that's simply going to be my force, now as a function of x, since it's changing, times every little infinitesimal piece. So this f of x dx you can kind of think of as dw. It's the infinitesimal amount of work we're doing when my force at a given position x is changed by a small incremental amount, dx. And then, of course, we will have definite bounds of where we are specifically changing it. So this is changing from a point x equals a to x equals b is our total distance we've changed. So the first example we see of this, perhaps the easiest, is Hooke's law, and this is with springs. So Hooke's law says that the force on a spring, and we'll say the force required to maintain or hold a spring a distance x from its equilibrium and this is stretching or compressing. So wherever it's equilibrium, if I compress it or stretch it, doesn't matter which direction, the force is then proportional to the distance we move it, to the distance we stretch or compress it. So in other words, the force on a string, or excuse me, on a spring is kx, where K, we call it the constant of proportionality, or the spring constant. So let's do a basic problem with this. So suppose we have a force of 40 newtons is required to stretch a spring from 10 centimeters, with 10 centimeters being the equilibrium, to 15 centimeters. We want to determine how much work is done stretching the spring from 15 centimeters to 18 centimeters. Okay, so not sure who taught you guys Calc 1, but whenever you're given a word problem, always helps to pick out key pieces of information. Step 1 with a word problem should almost always be draw a picture. So we have some sort of spring. Maybe it's attached to a wall. And its equilibrium is 10 centimeters. And when we stretch that to 15 centimeters, we need 40 newtons. And then, of course, we want the work done from 15 to 18. So let's write down some things. So my step 2 is almost always assign variables. But you also, for these types of problems, let's kind of write down relevant equations. As well as, I will say, conversions as well, because these are actually important, especially for work problems. So let's just kind of write down things we are needed. It's a spring constant problem. And so the equation we just had was that the force on the spring is proportional to the distance. And let's write down some conversions. So some things we may know or may not know. What is a Newton? Does anyone know this one? Do you remember from physics? So 1 Newton of work, or 1 Newton of energy, is the energy that it takes, or excuse me, 1 Newton of force is the amount of force it takes to accelerate 1 kilogram by 1 meter per second squared. So if we accelerate by 1 meter per second squared, or constantly accelerating by 1 meter per second squared, and it's a 1 kilogram mass, it gives us 1 Newton. So we have kilograms, and of course, the key thing to pay attention to is that here we are using meters when we are given centimeters. Likewise, we measure we measure work in joules. And joules is just 1 Newton force applied over 1 meter. So these are just our measurements for force and work, just units that we're using. Likely we will be using the metric system for all this, and not any crazy units of force like horsepower or anything like that. So we want to convert things to meters when necessary. One thing I'm going to add in here that's not going to be terribly relevant for this problem, but it will come in handy for future problems. Since we've drawn a picture, we've write down relevant equations. Choose a reference point. Because a lot of these word problems aren't set up on a coordinate frame, we're going to have to apply some sort of coordinate frame. And in a lot of problems, you're going to get different looking integrals based on where you choose your reference point. The answer should ultimately be the same. You just have to figure out all of your equations, all your geometry based off of where you choose your reference point. So in this case, our reference point, it's pretty natural, right? We should choose our reference point as just somewhere over here, right at the end of the spring. Since the information we're given is that 10 centimeters away is its sort of natural resting point, so it'll sit here at 10 centimeters, and then if I stretch it to 15, we have a force on that. So that'll come into play in some of these future examples a little more so. Okay, so we've got our reference point, we've got our equations. Now, I mean, kind of the next steps are like being able to set up the calculus, solve for the equations, solve for constants, and essentially just solve the problem. Let's see, I'm going to say set up equations and integrals. And then, of course, the next step is solve. Calc 1, there's some extra kind of steps in there because you're usually taking derivatives, especially with related rates problems. You're setting up your equations first, then finding more sets of equations based on the derivatives and how the derivatives relate. Not too big of a thing here. Usually we just have to kind of figure out things like constants. We'll have to figure out moments or centers of mass and things like that in future problems. So what's our equation? So we have the sort of general reference equation we start with, F equals kx, because we're in a spring, and what is the specific information we're given? So a force of 40 newtons, so this is a force, and if it helps, highlight, do things like this, write the problem itself. All right, I know that 40 newtons is associated with a force. Of course, there's my equilibrium, and then this is sort of my distance there that we stretch to, 15 centimeters. Okay, so be careful, right? Our x here is our distance from equilibrium. So what is our equation going to say? It says we had 40 newtons is equal to K times the distance from equilibrium. And again, since I'm using newtons, we want to make sure we're using meters for that. So since the problem was given in centimeters, our distance from equilibrium was 15 centimeters minus the 10 centimeters from equilibrium. In other words, 0.05 meters. So 40 newtons equals K times 0.05. And so my K is 40 divided by that. Unfortunately, it looks like some of these homework problems might need calculators, or maybe we just have to do that by hand. So 40 divided by 5 is what? 8 times, and then I'll have 10, and then I'll have 2 powers of 10 in the bottom. Yeah, so it should be times 10 cubed. So 8,000. And of course, the units there are going to be newtons per meter. So everyone see how I did that. Actually, wait, do I have an extra one? I do. I have an extra power of 10. Should just be 10 squared. So all I did was write the denominator. It's 40 over 5 times 10 to the minus 2. So sorry for squeezing that in there. Of course, 10 to the minus 2 will come into the numerator and give me that 10 squared. 40 divided by 5 is 8. So just some quick mental math without having to do a calculator there. So we found our K, and now what does the problem ask? Problem asks for work. It's always a key thing to pick out of problems. Calculus, don't think you guys are too bad with this, but there's always a statement at the end of the problem that says how much something or find this. Never hurts to underline, highlight that sentence. How much work is done is ultimately what we're trying to find. And then of course, I'm given my bounds from 15 centimeters to 18 centimeters. So our work, if we want to set up our generic equations, is the sum of every infinitesimal piece of work, every amount of work I'm doing, stretching the spring just a little bit. And so what is that? That is going to be the force at a given position x times every infinitesimal little piece of distance that I change, that I move with that force. And so we found our force is kx, and our k was 800 x, and then just dx. And we are stretching from 15 to 18. So careful, put those back in meters, so 0.15 to 0.18. And it looks like we might have to use a calculator to evaluate that. So the work for that integral is not too difficult. Of course, what do we get? We get 400x squared from 0.15 to 0.18. And actually, let's just write it like this. Squared. So whatever that ends up being. And typically with a lot of these problems, sometimes we'll just even have you set up, and once you get to the actual integral, that's kind of like the key bulk of the work. We challenge your skills of integration and being able to integrate that in other problems where the numbers aren't aren't awful. Okay. So next example is pumping fluid out of a tank. These are common problems that you see a lot in Calc 2. And so what we have is an inverted circular cone of height 10 meters and radius 4 meters. Is filled, we'll say, with water. Up to 8 meters. So find the amount of work done pumping water out of the tank. So picture, got a cone, inverted, so it's sitting like this. We are given the height and the radius. So the radius is 4 meters and the total height is 10 meters. We fill it with water up to 8 meters. And so what we're doing is we're going to take this water and we're pumping it out just out of the top of the tank. Be careful with this problem. Sometimes they have like a little spigot that adds extra height to it, and that's going to change the amount of work done. So that's the picture. Relevant equations and conversions. I would say in step 2 as well, labeling variables isn't bad, or like labeling sides, which we kind of do in part 1 as well. Let's kind of pick out, let's think of what equations are going to be useful for this. So there's no spring constant or anything, but what we want to think about is, well, how is work being done? Each sort of drop of water, so to speak, has a certain amount of mass, and it's being affected by gravity. So gravity is pulling down on it. And so when I have to pull it out, there's, I have to put some force into it to lift against gravity, and that the distance I have to go vertically is going to contribute to the amount of work I have to do. So let's see, some relevant things. We're going to need some sort of mass or density of water. We usually denote this by the symbol rho. And rho is given as 1,000 kilograms per meter cubed. Another unit you will commonly use for rho is just 1, but that's in grams per cubic centimeters. So a cubic centimeter is a cc. It's also a milliliter. You hear that tossed around anytime you get a shot or something like that, or get an IV. And water specific weight was kind of basically designed it so that we chose these measurements so that water was 1. But since we're using meters, we want to convert that to kilograms per meters. So that's our density of water. So what is density? Density is sort of a mass per unit volume. So we're going to need some sort of weight of water. Let's come up with our equation for force. So what is causing the force in this case? It's going to be the mass times gravity. Is really what's causing the force on there. We know gravity, or at least hopefully you know gravity, is 9.8 meters per second squared. And so now we just need an expression for mass. Let's see, is there anything else we're going to need? Not quite yet. So what is mass? So this depends on how we're going to cut it up. So since the force is always downward, then only the upward distance that we travel, or that we move the water, contributes to work. So that's kind of a key statement there. Sorry for that being off camera. So what does that mean? That means if I have a little drop of water over here versus a little drop of water over here, when I pump these straight up, even if I take this drop of water and move it sideways and then move it straight up, because moving it sideways theoretically doesn't really, there's no force required to do that. Of course, depending on where it is in the water, if I took a little piece of water, there'd be some sort of fluid pressure or viscosity that I would have to move against. But since we're kind of moving it from the top, when we pump it, we kind of think of maybe pumping it from the top down, that there's not going to be force required moving, an infinitesimal tiny drop horizontally and then upward. It's essentially going to be the same amount of work as just putting any drop upward. So in other words, horizontal slices let's say have a fixed amount of work. Needed to pump out the top. So sorry for getting off there. I'm trying to go back and forth between what I'm writing and this picture up here. So that means what we're going to do is cut this guy up into horizontal discs. Very similarly to what we were doing the past couple days. And on this disk, the force is constant, right? It's horizontal. So the net force on this at any given point, the force moving downward is the same, and the distance that I would have to move it is the same, the distance, vertical distance. Okay, so that's our setup. We've got our equations. We've kind of got our idea of how we're going to set this up. We have kind of set up this idea of these horizontal slices. These are our infinitesimally thin little slices. Now let's apply our calculus equations and set this up. So first step, or the next step I wrote, was to choose a reference point. And this is where our equations can look different depending on where you want to choose the reference point. So any input from you guys? Do you guys want to choose one yourselves, or do you guys just want me to kind of talk it out? So there's two natural reference points. The water level is changing, so we don't want to choose it at the water level. That would be weird, especially because even at this top of the water level, we have to move it. So the two choices that are going to be the best are either going to be the base of the cone or the top of the cone. Either one is going to work. It's going to look differently, though. Your integral is going to look differently depending on which one you choose. So let's do both, and then maybe we just set up the integral, and I'll leave it to you guys to figure out the rest. So let me get a new piece of paper, and let's redraw this picture so we can have it for reference. We've got our cone, height of 10, and the radius was 4 centimeters. And then, of course, the height of the water. Sorry, these were meters. And we are taking these horizontal slices. So let's pick top as our reference. I would say you also need to pick an orientation, so to speak. This is kind of similar to how we're assigning variables to problems in Calc 1. So for each disk, we want to pick some notion of measurement of how far it's going to move and give that a variable. So let's say y be the distance the disk is below top. So this distance here is y. And so I'm going to set this up. I'm going to say my work is the integral of dw. Not a bad way to start. And then what's that going to be? Well, it's going to be my force times the amount of change I would have to move each disk. So it would be upward times dy. So starting off this way, it kind of lets me know now that we need some notion of what is the force. So that's kind of our next indication of a piece we need to find. Well, our density of water is 1,000 kilograms per meter cubed. So the density, or the force, is going to be the density times the mass times gravity. Density times mass is going to give me the total mass, or excuse me, density times, not mass, times volume. Is going to be the total mass, then times mass times gravity gives me the force on it. So since we're cutting it up horizontally, my volume is going to be the volume of a disk. So let's keep our rho and our gravity as constants. Let's just leave them as it is, as constants. And then our volume of the disk is going to be the radius squared times pi And if you want, we're kind of getting a little redundant with these differentials. If you kind of want to think of the height of it as a dy, you can. We also kind of are considering the dy as every infinitesimal inch we move it. Of course, those are both essentially kind of the same thing, because we are kind of moving those each infinitesimal little disk upward. But the key important thing is, well, now I need an equation for the radius and how the radius of the disk is changing. So actually a better notation might have been something like rho g pi, the radius as a function of its depth, y, is what we need. Okay, and so based on our picture, the depth is y. How do I figure out the radius at a depth of y? This is where we got to do some geometry and do some work involving the height and the radius. So if we kind of pick out our triangles, I know that the entire thing has ratios of 4 and 10, which means at a given water level, if this distance is y, then that means this distance is 10 minus y. And what we need to know is the radius of the disk. And so we can just set up similar triangles and say that the radius over, so however you want to set it up, let's set it up with corresponding signs. So the radius relative to the big radius should be the height of that triangle relative to the bigger height. So solving, we find that the radius as a function of depth is going to be 4/10, so 2/5 times 10 minus y. Okay, so I think that's all of our pieces. We're going to have to square that guy and then plug everything in. So now what is our work? in this case. What did I do? That's what I'm doing wrong. This dy shouldn't be there. So sorry, let me recorrect this. Kind of got into a little brain fart there. That's why I was ending up with extra differentials. So our work integral of dw, what is the infinitesimal amount of work done in moving one of these disks out? Well, the total distance we're moving it, since I set it up at a distance y below the origin, the total distance I have to move a disk is y. So if the force is constant on that disk, then I'm moving at a total distance of y. That's an infinitesimal piece of work that I've done for that amount of water. My differential then comes into play with the width of the disk there. So the work should be let's see, we got rho, we've got g, we've got pi, those are all constants. We've got our radius, squared for the area, and then I'm moving that a distance y, and the dy comes into play from the width of those guys. And then the bounds we need, and the bounds we find specifically relative to the reference point. So our y was measured downward. So if we want to think of y extending downward, y increases as we extend downward. The smallest y we start at is 2 centimeters. And then the largest depth we go down to is up to 10. Does that make sense? Any questions on this guy? Okay, so for the sake of time, I actually kind of. Oh, sorry. Go ahead.
Sorry. Yeah. So, where did the y come from in your equation at the very end, right before the dy?
Yeah. So sorry, I realized I was missing something. So the reason we need to set up this y is because that is the distance we're moving. A better way to write this, or another way we might want to write this, as like df times y. Because there's, on these infinitesimal little slices, there's sort of an infinitesimal amount of force on it. But we assume that for each slice, at a given depth, that force is constant. And so I have to move this slice a total distance of y to get out.
Okay, I see it.
And so maybe we'll come back to this one again, or maybe we'll try another one of these examples. These examples like to come up a lot on quizzes and midterms. And so we can try, there's different shapes of the trough that we're trying to pump water out. And we can try different ones and try to pick different reference points. For the sake of time for today, though, I want to see some more different examples because we need to do hydrostatic pressure. And if we have any time, maybe start to talk about centers of mass. So let me just write down the example, and then we'll try to pick out all the pieces as we've kind of done with the past two problems. So suppose we have a trapezoidal dam. And I'm just going to draw the picture. It has total height of 20 meters. It has 30 meters in the base, 50 meters at the top, and then we have water filled 4 meters from the top. And so the question is, what is the hydrostatic force of water on the dam? So what's happening, like the idea behind this is at every given depth, there's more and more pressure, right? If you're a deep sea diver, the deeper you go, the more pressure there is. And that pressure is pushing in all directions. So even if I'm on the edge of this dam, the deeper I go, essentially the more water pressure there is pushing out onward to in the front of this dam. And so what we want to know is how much total force is there from this water on this face of the dam. So this is our picture. Relevant equations. So the force, in this case, it's again mass times gravity, which is going to be the density times the now area times gravity times the depth. And so the deeper we go, the more pressure there is. And so if we cut this guy up horizontally, then at whatever depth the water is at, there's going to be more force. And then at that fixed depth, I mean, since we want to slice it horizontally again, because slicing it horizontally, we'll have a fixed depth, and then we can figure out the total area of that to sort of add up all of the force on that. And we just have to multiply times rho, times the density and gravity. Okay. So, what is our force in this case? So let's pick a reference point. Again, we can pick either the bottom or the top as good reference points. Again, though, because we are sort of increasing our force as we go downward, it's almost better to pick the top as our fixed reference point. So let's pick the top. As our reference. And actually, you know what? In this case, so we're not, actually, you know what? Let's pick a different reference point. So why would the top may not be the best in this point? Let's say top of the water. Since we're not actually pumping the water, I'm not trying to move the water up an additional 4 meters out of this. Really what we're measuring is just the depth, but where's our reference point from the depth? Let's say pick top of the water, since this is where depth is measured from. And since the force depends on the depth, it'll be a natural choice, since then we won't have like a linear shift. If I pick the top here, it wouldn't be bad. It's just that where does the depth of the water start? It would be 4 meters plus whatever depth we are below that. And we would just have to make sure we take that into account. So what is our force? So our force is essentially our pressure times the area. So this is another equation that our pressure, it's kind of generic, that our pressure is just the force per unit area. So of course, naturally the force is pressure times area. And if I am slicing things up, the pressure is essentially constant for every infinitesimal piece of area we choose. Let's call this a dy again. And actually, so that is our depth. Let's give it the variable of y. Just so I'm not writing like dd or anything like that. And of course, this force we can also kind of consider in many ways just the infinitesimal amount of hydrostatic force on a given slice. So our net force, our total force, is to add up all the infinitesimal pieces of force, which is going to be the pressure as a function of depth times the infinitesimal amount of area that each of these slices occupy. Okay, so what do we need? We need the pressure as a function of depth and the area of these guys. So the pressure is essentially just the mass times gravity times the depth. So if I take the total force and of course divide by area, we get our mass, or our density times gravity times the depth, which I will now label as y. And then we need our dA, is the infinitesimal piece of area from each individual slice. So this one we have to do a little bit of geometry again with this. So this one we could come up with equations for these lines based off of the reference point, or we could try to just use a little bit of geometry equations to figure out what's going on here. So let's draw the picture again. So we were at 50 meters at the top, 30 meters at the bottom, and the height was 20 meters. So we kind of want to figure out, well, what is the net change as I decrease? Or what is sort of the rate of change of the width of this guy as I decrease a distance of y? So, well, how far does the width change? If I'm starting here at the top and I decrease by 20, the total width decreases by how much? Oh, sorry, that's not on the video. If my total width at the top is 50, then decreasing the height by 20 decreases the width by 20 as well. So in other words, since that rate of change is constant, then if I decrease by y, then the width decreases by y. Does that make sense? You can kind of set it up. It's essentially sort of similar triangles, but for trapezoids, you can kind of imagine if we wanted to extend this into a triangle, I want to know sort of the ratio of what's the change or what's the relative ratio of decreasing my width to decreasing my height. And so if I change the height, so my delta height relative to delta width, if I change the height by 20, then the change in width goes from 50 to 30. So they just change in a 1-to-1 ratio. Meaning if I'm at a distance now, let's say this height is going to be, sorry, let's go back to our original picture. If I am at 4 meters below the surface, then the width should be 4 meters less than what I started with. So wait, if I decrease the height by 4 meters, I am decreasing the width by 4 meters. So the width is 46 of where we start. Was that clear? So again, you could use similar triangles, essentially pick out the geometry like we did, or if you really want to, you could come up with equations for these lines and model it that way. Okay, so let's finish setting up this problem. We had that the force is rho gy times dA, which is going to give me a rho, a gy, and then dA now is, so at a depth of y meters below my reference point. So if I am starting, the starting width, as I just mentioned, was 46. And then if I'm going y below that, the width of this bar is going to be 46 minus y. And then, of course, the height is just dy. And then what are the total y ranges we're working under? Since I'm starting here and then working downward, starting at a distance of 0 depth, and then my depth goes all the way down to 16. Does that make sense?
This is definitely not a proper limit. That's more like a pin. On this side, we're really no better. This is just useless and horrible. This one
John, sounds like you got a video playing there, man.
actually, like, that's good. That means there's one rivet on this side at least that's going to hold.
All right, so no questions on that guy. Let's go ahead and move on. Let's take a look at centers of mass. So if I have some reference point, let's call this my origin, and I've got mass 1 at a distance of x1. I've got mass 2 at a distance of x2. Let's say we've got a third mass. A distance of x3 from the origin. We want to know where the center of mass is. We denote it by x bar. In other words, it's sort of like the average x value that all of these masses are away from the center, but it's relative to their weights as well. Think of it like a teeter-totter. I want to know where the balancing point is for all these weights. Is sort of the x coordinate of the balancing point. So it may not be the origin. It might be somewhere here, depending on the weight of the masses as well as the distance, right? If mass 3 is really light, well, it's still really far away, and you can imagine with a larger lever arm, it's still going to weigh that side of the teeter-totter down. And so the two things we need to keep count of are the distance and the weights. And so how do we figure all that out? Well, it's just sort of the sum product, so to speak, of all the weights. We are essentially taking every individual mass, mass 1, times its distance from the middle. And I want to add all of these up. And then divide by the total mass. Where, in some sense, does that come from? If we split up this sum, you can think of it as mass 1 divided by the total mass is like the proportion of the total mass that mass 1 is, and then weighted by its distance from the origin. Then add mass 2 divided by the total mass, which will give me the proportion of the total mass that mass 2 occupies, weighted by its distance from the origin. So how do I turn this into, well, a calculus problem? If instead of individual masses, we had a string that was of varying density, so let's just say we have a one-dimensional with varying density. We'll call it rho of x. So we just have a string, but some parts of the string get kind of heavier, where it might be thicker or it's just denser in some parts, and then it gets lighter. Or you can kind of think of it as like a string or like an iron bar or something that's not uniform. Some parts are not as dense as the others. And so where is my center of mass going to be for the bar? Well, it's not necessarily going to be in the center of the bar. Let's actually draw a bar here. And you can kind of think that some parts are lighter and then some parts get heavier. And then some parts thicker, lighter. Well, essentially we want to turn this into a weighted integral. It's going to be the integral of the distance, so wherever we pick our origin at. And then we can kind of think of cutting the bar up into infinitesimally thin slices. They're a distance x from the origin times whatever mass. If I cut out a slice, well, that's going to have an infinitesimal amount of mass. That's equivalent to sort of one of these blocks having its own mass. Except now, instead of blocks, I kind of have to create my own slices out of it. And so what is that going to be? Well, it's going to be the area or the volume of it times the density. So area or volume, depending on how many dimensions you're working with in this bar. So in this case, if it's just like a 2D bar or even a 1D bar, it could just be a dx in this case. But this is just the numerator here. So we still actually need to divide by the total mass. So all in all, our x bar, we actually have to compute two integrals. We need to weight every piece of mass by its distance from the origin, and then divide by the total mass. And how do I find the total mass? Well, if it's varying density at every given point, the total mass is just summing up the density, the infinitesimal amount of mass we have at every given slice. And these bounds will be from whatever the length are. So let's say our origin was here and the length was L. So that's the general idea. We do have more complicated things going on in Calc 2, because now we have some 2D shape. Where the curve is given by y is equal to f of x. And what we want to find is not just the x coordinate, but the y coordinate of its center of mass. And so now what do we have to do? Let's introduce some notation just to simplify some things. So we have y equals f of x is the shape. And then assuming that, now in this case, because we have a shape, we have some constant density. rho, and whether that's a mass density, sometimes it's a mass density or a weight density, and then of course constant gravity. Depending on whether we're using metric or imperial. Usually I think if we're using metric and we're just finding mass and we're not giving weights, I don't think we need to worry about gravity. So then we want to come up with the equations for center of mass in terms of x and y. So x is going to be similar. So our x bar is going to be, so we pick some sort of origin. And well, where's the center of mass of sort of every given piece? In some sense, we can consider this whole thing, this slice, as an infinitesimal piece of mass. So my x bar is going to say, take, oops, screwed up my notation. Weight each piece of mass by x times the density times the area. So density times area is like dm, my infinitesimal piece of mass. And then, of course, divide by the total mass. Which is just the density times the area. So let's pick each of these out in parts because they're a little tedious to write. This top part is called the moment of inertia about the y-axis. This bottom part is just our total mass. Why do we call it the moment of inertia about the y-axis? Well, you can kind of imagine that if I just fix the y-axis, I'm measuring how far things are away from the y-axis. This moment of inertia, in some sense, gives me a measurement of how hard it is to rotate something about the y-axis. And since I'm taking these slices that are parallel to the y-axis, this given slice is always the same distance from the y-axis. So it'll have sort of the same amount of energy, so to speak, required to rotate it about the y-axis. And as I move further from the y-axis, you can kind of imagine like the centripetal force increases, right? Think of like swinging a yo-yo or something. As the longer the string gets, the more force that's required to kind of whip it around this central axis. And so let's just finish this up real quick. So my moment about the y-axis is going to be x. dA, so what is the area of this guy? It's just going to be the height times the width. Likewise, our y bar is going to be the moment about the x-axis divided by the total mass, where the moment about the x-axis, well, what is that? Well, now I want to know how hard it is to bend each of these around the x-axis. So we kind of think if we're just working from the center and rotating it around, it is essentially, again, it's going to be its average distance, which is 1/2 f of x. If we consider the slice infinitesimally thin, then the height is going to be half of the, or center of mass is going to be half of the height, and then times the area, dA, which again is just f of x dx. So the moment in the y-axis, we can pull the rho out, we can actually pull the 1/2 out, and then it's going to be f of x squared dx. Okay, so we're a little bit over time, so sorry about that. We'll continue with this tomorrow, and we will see some more examples with this. Stick around if you got any last minute questions, and I'll be able to stick around for like 5 minutes or so maybe.